Let's jump right into this explainer and crack open the ultimate toolkit of the 8086 microprocessor, its instruction set. If you've ever wondered how our high-level human intent gets translated into microscopic, lightning-fast physical actions inside the chip, well, you're in the right place.
It is honestly wild to think about, but every complex action this processor performs, it all boils down to just 117 fundamental instructions. That's it, just 117 commands making up this incredibly concise vocabulary that literally forms the basis for infinite computational possibilities. We'll be moving quickly today through the language of the 8086, how we move and calculate data, logic, bits, and strings, controlling program flow, assembler directives, and finally, bringing it all together to build a complete program.
Section 1. The language of the 8086.
So the processor's capabilities are divided into 6 core groups, almost like departments in a factory. You've got data transfer, arithmetic, bit manipulation, string handling, program transfer, and processor control. They all work together seamlessly to get the job done. But there is one absolute golden rule you've got to remember. Direct memory-to-memory operations are a no-go in the 8086. Data always needs a middleman, like a register, to actually move around.
Section 2. Moving and calculating data.
Think of your data transfer commands as the heavy lifters of this whole operation. The MOV instruction is basically your standard courier, copying bytes or words from a source over to a destination. Then we have push and pop, which are actually super cool. They act exactly like those spring-loaded plate dispensers at a buffet. Push stacks a 16-bit word right onto the top of the memory stack, and pop grabs whatever happens to be sitting on top. Toss in XCHG for instantly swapping data, plus in and out for talking to external ports, and you've got the whole logistics team ready to go.
Now, once the data is securely on the floor, the arithmetic crunchers step in. You know the basics. They can add or subtract, or use INC and DEC to quickly increment or decrement a value by exactly 1. But I want you to pay special attention to CMP, or compare. This one is a really clever instruction. It subtracts the source from the destination purely to update the processor's condition flags, without actually altering your original data. It's essentially like weighing a package to see what's inside without ever opening the box.
And here is a great example of how the 8086 handles the nuances of math. When it multiplies numbers, context is absolutely crucial. It uses MUL for basic unsigned numbers, meaning strictly positive values. But it has to switch gears to IMUL, or integer multiply, when it needs to safely account for both positive and negative signs. It's a subtle distinction, sure, but absolutely vital for keeping your calculations accurate.
Section 3. Logic, bits, and strings.
Way down at the microscopic level, before we even do basic math, we often need to merge or filter raw binary data. That's where logical gates come in. Instructions like AND, OR, XOR, and NOT let the 8086 compare binary patterns bit by bit. Take the OR instruction, for example. If either the top bit or the bottom bit is a 1, boom, the resulting bit becomes a 1. It is just an incredibly fast, efficient way to mask or combine specific data points.
Now, when we're shifting these bits around, the really crucial part is preserving their original meaning. Let's say we shift bits to the right using the SAR instruction, which, by the way, is a super fast way to divide a number by 2. The 8086 is smart enough to preserve the original high-order bit, which represents the sign. It shifts everything over, but it copies that leftmost bit into the empty space left behind. That guarantees you don't accidentally turn a negative number into a positive one just by doing a quick division.
But what if you don't want to lose the bits falling off the edge? Compare a shift to a rotate, like ROR, or rotate right. Unlike a shift, which just drops bits off into oblivion, a rotate instruction catches the bit falling off the right side and loops it straight back around to the front. And at the exact same time, it generously copies that falling bit into the carry flag for safekeeping. Nothing is lost. It is a perfect circular loop.
Of course, sometimes we aren't just dealing with single numbers. For handling text and larger sequential blocks of data, the 8086 steps up its game with string operations. You've got MOVS for moving strings and SCAS for scanning them. But the real magic? The real magic happens when you slap the rep or repeat prefix onto these instructions. Doing that converts a single, simple command into this powerful, auto-executing loop that just churns through memory until a specific termination condition is met.
Section 4. Controlling the program flow.
Okay, so to control the flow and keep our programs from just running in a straight, boring line, we need decision makers.
A standard JMP or call instruction unconditionally moves the program to a completely new location. Simple enough, but check out conditional jumps, like JZ for jump if 0 or JC for jump if carry. These are the smart managers of our factory floor. They actually look at the status flags updated by your previous operations and branch the code only if those specific conditions are met. This right here is exactly how the 8086 makes choices.
Section 5. The assembler directives. All right, before we write any code, we have to talk about assembler directives. It's really vital to understand that directives are never, ever executed by the 8086 chip itself. Instead, they are statements that give directions to the assembler program, the software that's translating your human-readable assembly language into the ones and zeros of machine code. Directives tell the assembler exactly how to organize memory and structure the entire file.
To give you an idea, by using directives like db to define a byte or dw to define a word, you're actually reserving space and memory for your data beforehand. Or you can use EQ to equate a specific text label to a hard-coded value, which just makes your code way easier for humans to read. And obviously, the end directive tells the software where the program officially stops. You are setting up the architectural rules before the hardware factory floor ever powers on.
Section 6. Building a complete program.
So, we've seen the raw commands and we know the rules of the assembler. The big question is, how does our human logic actually look when it's formatted perfectly for the 8086 processor to execute? Let's bring it all together.
Let's walk through a complete sequence for adding two 16-bit numbers. Just notice the logical flow here. First, we load the initial data into the AX register using a move instruction. Then, we clear the CL register so it's completely ready to handle any carry overflow. Next, we perform the actual add instruction. And finally, we safely store that result back into a specific memory location. It's step by step, and it's perfectly orchestrated. And if you look closely at the anatomy of that code, every single line is elegantly structured into 4 distinct columns. First, you have labels acting as reference points. Second, the mnemonics or opcodes telling the machine exactly what to do. Third, the operands telling it where to do it. And fourth, crucially, you have comments on the far right, gently reminding the human programmer why on earth we're doing it in the first place. It is truly mind-blowing to realize that all modern software logic, from the device playing this explainer right now to the massive servers hosting it, is ultimately built upon these simple, foundational actions rapidly executing in sequence. The 8086 absolutely laid the groundwork for the digital world as we know it. So, now that you understand the raw elements of this ultimate toolkit, what world are you going to build with it? Thanks for hanging out with me for this explainer, and keep building.